So, welcome everyone. Thanks for being here. This is our second doctoral meeting on aerospace, on the PhD program on aerospace science and technology. Today we're going to be discussing about propulsion and the space environment. We have 7 presentations of 7 PhD students, namely Alberto Marin, Alberto Modesti, Enrique Bello, Jesus Perales, Marco Ricardo Inchingolo, sorry for the pronunciation, Pedro José Jiménez, and Tatiana Pegotin. They are doing different PhD theses on um, electric propulsion, both numerical and experimental, and they're going to be telling us what they have done so far in the first, second year of their PhD thesis. The goal of these doctoral meetings is to gather together, to get to know what the PhD students are doing, for you PhD students to share your progress with your supervisors, a qualified audience in the department, faculty people, but also your peers, other PhD students, so that you can also get to know what others are doing, have discussions, and foster collaborations and exchange of ideas, which is a very important part of our research. So now, having said that, I would like to thank you all for being here.
So I'm going to present my thesis work now, which is the name of the thesis is Fluid Kinetic Models for Space Plasma Thrusters. These are the contents of the talk. Firstly, I will go a brief introduction of plasma thrusters, which will complement what my colleagues have already said. I will go very fast over them. Then I will talk about the state of the art and motivation. I will present very briefly also, because they have been presented, B2 Plus and Hyphen, the codes I have been working with and I will still be working with during my thesis. And I will show some results, and finally I will conclude with conclusions and future work. So I think I haven't been mentioned yet, but one of the main interests of using plasma thruster or electric propulsion is its high impulse compared to chemical propulsion. You can see here in this chart what is the high specific impulse of electric propulsion compared to chemical, and basically these allow us to reduce the propellant consumption. So in principle, electric propulsion is not energy limited, and however there is a limitation in terms of the thrust. You can see it here. That is related to the limitation in power available on the spacecraft. So yeah, we see that every day that electric propulsion becomes more and more important in the space field. Even if it is already a mature technology, every day it takes a bigger market share in the space field. And here I present just some news related to this. Well, the working principle of plasma thrusters is basically the production and acceleration of charged particles by means of electromagnetic fields. And this is the way in which we can achieve such a high ISP that I showed before. My thesis will work mainly in two thrusters, which are graded ion thruster and Hall effect thrusters, that I think have already been they have already been presented very good manner by my colleagues. So I will not enter into the details of them. I just want to mention that they are already, these two thrusters are already a mature technology. They are flying since the 70s. But even if they are a reliable and high efficient technology, there are still part of the physics that need to be investigated because they are not well understood. And also we find that the design of these thrusters and the development of these thrusters is highly dependent on previous flight data or in costly experimental tests. The need for numerical tools, for numerical simulations to work on the design and development of these thrusters is clear. And we always aim in the field of numerical analysis at predictability, although we see that this is a very difficult task. Regarding the research gaps we identified and the ones in which we focus along in this thesis, well, there are certain topics that haven't been enough deeply studied with simulations, Those can be, for instance, the study of complex magnetic topologies in Hall effect thrusters. I will show actually some results of this. The interaction of plasma with vacuum chambers, also the dynamic response of thrusters when they are submitted to dynamic control inputs. And also, for instance, we have also a very interesting field of analysis, which is the effect of electron inertia and turbulence. Although this, the effect of turbulence or anomalous transport cannot be fully understood with fluid models in terms of electrons, and thus my work need to be complemented with the studies of Alberto and Enrique, which have already presented, who have already presented their works. So among the different approaches to simulate plasmas, I will be using, and I have been using a hybrid peak fluid approach, which you see defined here, and my colleagues have already defined, in which we treat ions and neutrals, the heavy species, as macroparticles, and electrons as a fluid. This is a trade-off in accuracy and time. So just to complement a little bit what my colleague said about peak codes or particle insert codes, I just wanted to mention that what we do in a peak approach is basically a discretization of the velocity distribution function here in the Blasov equation. We discretize this velocity distribution function into superparticles that follow simple dynamic relations. Here you see simple Newton law and kinematic relations. So regarding EP2 plus and hyphen, my colleagues have said already a lot about them. As I mentioned, I will be working on these two codes. The day-to-day work of my thesis basically consists of further developing this. And I'll show some examples of these developments in a second, and also to run simulations with these codes of real thrusters and compare the simulation results to experimental data that we are provided with. So in the end, the goal of the general goal is to study the topics previously introduced by means of these tasks. So my work mainly focus on working with hyphen, but some initial work has been done with EP2+. So I will start presenting that initial work with EP2+. So I'm already talking now about the results of some of the results of my thesis. So with EP2+, I studied initially at the beginning of my thesis a gridded ion thruster. You see here the domain for which I solved the grid ion thruster. So I solved the problem of ion optics, which basically is the problem of the grids, of studying how the grids focus and form the ion beam. So for this, I needed to modify EP2+ slightly because EP2+ was focused initially on plasma plumes. This was partially done in during the time of my master thesis. And also, I introduced the electron inertia term in the momentum equation for the electrons, and I added its effect. Also, in the realization of this work, I worked with different approaches. You see here infinite versus finite approaches. This infinite approach, although there's only one hole simulated, the symmetric boundary conditions that are imposed here, you can see them also in the lateral boundaries. These boundary conditions, which are symmetric, model the interaction of this hole with the rest of holes, with infinitely many holes surrounding these holes. And we also worked with a 1D semi-analytical model that we proposed, and we compared the results of the numerical simulations with that 1D semi-analytical model. So the main results of this work, of this initial work in my thesis, basically are the following ones, the ones that I'm presenting here. We make a comparison and satisfactory comparisons of experiments and 1D model to numerical simulations. Here you can see how the 1D model this is just a small part of the comparison. But you see how the 1D model is good for a certain level of operation, for a certain level of operation of the ion thruster, which is characterized by this parameter. And also, I found out that the influence of inertia of the inertia is little on the currents, though it cannot be neglected a priori. And also, I studied the neutralization and formation of the plume in terms of current, in terms of current and in terms of charge, something which haven't been so deeply analyzed, mainly in terms of current. You can see here some currents that are obtained by means of the fluid model. And also I compared the two computational approaches I show here, the infinite versus finite approach, and we found out that the cheapest one, the cheap computational approach, which is the infinite limited holes, which is the one in which we simulate one hole. Well, we found out that they yield similar results, so we validated it. Regarding this work, a conference paper has been published, as well as there is also a journal paper that has been submitted and is currently under revision. Then my next step was to start working with Hyphen once I finished with EP2+. And with Hyphen, I basically have been working on the simulation of a Hall effect thruster that is called HT5K, which is a magnetic shielding Hall effect thruster. Magnetic shielding refers to a specific magnetic field topology that protects the walls of the thruster from erosion. You actually can see here the thruster while firing. So this work has been developed in the framework of EDA project, in which EP2 UC3M has been in charge of simulating the thruster. And well, the modeling of this HT5K has required several tasks. Among them, we can highlight the generation of magnetically aligned meshes like this. Previously, Alberto talked about numerical diffusion in Cartesian meshes. Well, it seems that for high magnetic field intensity, numerical diffusion is something important. So we worked with magnetic field aligned meshes to reduce this numerical diffusion. And also the solution of this complex problem of the HT5K plasma discharge has required the generation of a simple model of the turbulent a simple law of the turbulent or anomalous transport, for which we don't have a full physical comprehension, as Enrique and Alberto showed. But we have made a phenomenological model. We have made a simple law that is based on experimental provided by CTIL, and we have identified the level of turbulence dependence on the dependence of the level of turbulence, on the operation point of the thruster. And we made some simple laws that allow us to interpolate and obtain the level of turbulence from one point of operation to another. So the main results, well, already mentioned this identification of the level of turbulence. We also obtained results that allow a 2D time resolved characterization of the plasma discharge that is needed for the integration of the thruster with the rest of systems of the spacecraft. We also found good agreement with numerical we found a good agreement between numerical simulation and experimental data, which you can see here, down here, very briefly presented. And also, we very interestingly, we found the effect of the magnetic topology in our simulations. That was very clear. The existence of the magnetic topology in the plasma contours. You can see here, for instance, the temperature, the low temperature on the walls. This is a clear effect of the magnetic the magnetic shielding. When you have a very low temperature, erosion to the walls erosion of the walls is clearly reduced. And we also satisfactorily compared these results, the results obtained with the simulations, to other thrusters in literature. So regarding this work, a conference paper has been published, and there are also several. Well, there is also a journal paper being currently it's been currently written. So we will expect to publish it soon. And also within this framework of EDA and also with HT5K, a different topic we have been working in has been the study of the dynamic response of the HT5K thruster, something that hasn't been very deeply studied numerically. We found some experimental results on other thrusters, and we tried to reproduce those results in our thrusters, in the HT5K thruster. And well, first we made a step analysis of we analyzed the step response of the thruster to step changes in the input mass flow and the input source voltage, and we characterized the response types of the thruster, something which is important within the framework of the EDA project for the integration of the thruster with the rest of subsystems, mainly the electrical system. And most importantly, we studied the modulation of the source voltage. What is the meaning of this modulation of the source voltage? Basically, if we are able to input the source voltage to the thruster that is has a sinusoidal shape that is close to the frequency of the natural frequency of the thruster, the breathing mode. This is what the meaning of this is. We are able to find, as some experiments did, we are able to find some resonance properties, some resonance in the oscillations that increase certain efficiencies of the thruster, and we found this numerically. We could cross-check this to experimental results. We also found, by the way, that the total efficiency was not significantly improved. And just to conclude, I just have the progress on my thesis up to now. We are currently under the preparation of 2 articles based on the previous HT5 results, 2 journal articles that we hope to send very soon. And well, next steps here I've been very general. Further hyphen development. This can mean, for instance, the developments to study erosion or implementation of new algorithm for a Cartesian mesh instead of a magnetically aligned mesh, or implementation of electron inertia, as I did for EP2+, and things like this that would allow us to continue in to improve the simulations of Hall effect thrusters. And also the task for me will be the simulations of the HT320K thruster, which is also a Hall effect thruster with higher power than the HT5K, within the project called Aspire. And that's everything. Thank you for your attention, and I would be glad to answer any question you may have.